The James Webb Space Telescope, JWST, has unveiled a spectacular phenomenon: rays of illumination. Emanating from what appears to be an urban panorama seen from a point light years away. This revelation has reignited fascination with the potential reality of extraterrestrial life. The observatory centered its attention on Proxima Centauri B, the nearest known exoplanet to our solar system, and registered atypical radiant flashes of light. Could these indicators represent an alien civilization? Keep an eye out for more updates. For many years, researchers and the broader public have been enthralled by the idea of life beyond Earth. Any sign hinting at such life in the cosmos has been embraced with enthusiasm. But a pivotal development came when the James Webb Space Telescope disclosed persuasive signs pointing to the possible existence of life somewhere in the universe, while scanning the expanses of space. This mighty instrument located something remarkable on a distant exoplanet. It detected illumination similar to those from extraterrestrial metropolises, igniting speculation that an alien cityscape might be present on that far-off world. This idea has sparked massive excitement and intrigue within the scientific community, as it might represent the long-awaited breakthrough, suggesting the presence of intelligent entities operating societies in forms we are only beginning to explore. Witnessing these city-like illuminations from an extraordinary distance of 4 light-years away, NASA specialists are astonished, wondering how long these lights may have persisted until our era advanced enough to detect them. David Kipping, an astronomer at Columbia University, has described the planet where these lights were located as remarkably complex. Unlike standard rocky worlds that absorb starlight and emit energy as infrared radiation, this exoplanet exhibits unique behavior due to its one-of-a-kind interaction with its host star, Proxima Centauri. This landmark discovery highlights the James Webb Space Telescope's critical contribution. Its capacity to detect infrared wavelengths was essential in discerning the planet's atypical patterns, which is indispensable for comprehending its atmospheric attributes. Scientists intend to continue leveraging the telescope to study the planet's environment in greater depth, aiming to determine whether it might sustain life. The James Webb Space Telescope is especially sensitive to infrared radiation, enabling it to observe phenomena on Proxima Centauri B even during its nighttime cycle. Many telescopes struggle to capture faint glimmers in the cosmic darkness, but the Webb telescope excels in detecting even the subtlest luminescence. This capability makes it an ideal instrument to confirm whether the proposed city lights on Proxima B's dark hemisphere are real. The instrument can register artificial illumination in space, assuming it falls within a very narrow frequency band, notably tighter than the emission ranges of regular stars. Proxima Centauri B has a dynamic interaction with its star, which profoundly impacts its environment. Like many planets orbiting stars, it absorbs intense energy from Proxima Centauri. As the planet orbits, it experiences cycles of daylight and darkness, much like Earth. During the day, it endures blistering heat, while at night, temperatures drop drastically. The thermal range on Proxima Centauri B is vast, largely influenced by its composition. For instance, if it possesses an atmosphere, the temperature contrast between day and night could be extreme, scorching on one side and freezing on the other. Such dramatic thermal swings are a primary focus for astronomers, as they provide valuable insights into the exoplanet's atmospheric composition. That the James Webb Space Telescope, with its ability to image in the infrared spectrum, can effectively study the planet's thermal emissions, shedding light on its atmospheric traits. Fascinatingly, the telescope's orbit around Earth aligns with Proxima Centauri B's orbital period, allowing researchers to capture consistent observations of its illumination cycles every 11.2 Earth days. If Proxima Centauri B harbors an atmosphere, the next objective is to examine its chemical makeup to assess its habitability. Detecting molecules such as oxygen, water vapor, and methane could indicate that the planet might support life. This involves examining starlight as it filters through the planet's atmosphere. It's a sophisticated process. Even though the James Webb Space Telescope excels at characterizing planetary atmospheres, it was primarily designed for other scientific goals. Its strengths lie in measuring water vapor, carbon dioxide, and methane levels. Although it's less adept at detecting free oxygen, a crucial biosignature. Nevertheless, the telescope can still search for other critical markers, such as ozone, which indicates a robust atmosphere, as experts scrutinize the data from the James Webb Space Telescope. The search for distant worlds continues, bringing us ever closer to resolving whether we are alone in the cosmos. It's worth noting that JWST can only observe a limited number of exoplanets closest to Earth. For more comprehensive analysis of planetary atmospheres, astronomers will turn to ground-based observatories like the Extremely Large Telescope, ELT, anticipated to commence operations in 2027. The ELT is engineered to offer deeper insights into remote exoplanetary atmospheres, delivering sharper and more precise statistics on their capability to support life. Scientists eagerly look forward to the deployment of next-generation space observatories such as the ELT. Meanwhile, the James Webb Space Telescope remains an invaluable asset for probing far-flung exoplanets, regardless of its constraints. The Webb Telescope continues furnishing vital information that could reshape our understanding of what lies beyond our solar system. Researchers harbor ambitious goals for future observatories. They aim to develop technologies that reduce starlight interference, enabling improved scrutiny of orbiting planets, just as one might use their hand to block the sun to see more clearly. These upcoming telescopes will focus on the faint reflected light from exoplanets, facilitating more detailed study of their atmospheres and assessments of their habitability. However, this endeavor is far from trivial. Stars shine with such intensity that they completely dwarf the light reflected by their planets, complicating detection efforts. To confront this challenge, scientists are pioneering multiple novel techniques. One promising method is the use of coronagraph optical instruments embedded within telescopes that block stellar glare while allowing faint planetary light to pass. By carefully designing and shaping light waves, coronagraphs drastically reduce starlight, aiding the detection of tenuous planetary glow. Another advanced technique is the Starship, a massive, flower-shaped spacecraft deployed in tandem with a telescope positioned tens of thousands of kilometers apart. The Starship operates by physically obstructing starlight before it reaches the telescope, allowing only the planet's faint light to be captured. This technique promises to be particularly effective for observing exoplanets located within their star's habitable zone, where liquid water and life might exist. Still, these technologies demand remarkable precision. For instance, aligning a starshade with a telescope across colossal distances must be accurate within mere millimeters. Moreover, such systems must be compact, energy efficient, and robust enough to withstand the harsh conditions of space. Despite these challenges, the potential payoff is enormous. Successfully observing and analyzing exoplanetary atmospheres could unveil biosignatures, chemical indicators suggestive of life. Molecules like oxygen, methane, and water vapor in specific proportions might signify biological activity, offering some of the most persuasive evidence yet of extraterrestrial life. Researchers are also developing strategies to directly image distant worlds in greater detail. Future observatories may include sophisticated, adaptive optic systems to correct distortions from Earth's atmosphere or telescope instability, resulting in clearer, more precise images. Coupled with starlight suppression technologies like coronagraphs and starshades, these advancements could empower scientists not only to detect exoplanets but also to map their surfaces and observe their weather systems. Such imaging would mark a monumental leap in our ability to understand remote planets and assess their potential to harbor life. As humanity's journey through the cosmos continues and our capacities to observe and interpret distant phenomena evolve, the contributions of the James Webb Space Telescope and its successors grow ever more critical. Its unrivaled sensitivity to infrared signals allows it to detect even the faintest planetary emissions, dissect atmospheric layers, and pinpoint potential biosignatures indicative of organic processes. Thanks to continuous technological advances and a growing trove of astronomical data, humankind stands at the threshold of findings that may revolutionize our comprehension of life's role in the universe. The detection of artificial illumination, or SETI-like lights on Proxima Centauri B, our nearest known exoplanet, could mark the beginning of a transformative chapter in space exploration. This ongoing search is not solely about gathering empirical evidence. It also taps into profound philosophical and existential questions. What would it mean if we confirmed we are not alone? How might contact with another intelligent civilization alter our world? The excitement surrounding Proxima Centauri B serves as a powerful reminder of our innate curiosity and our quest for meaning beyond Earth. Future generations of observatories, whether stationed in orbit or on our planet, will continue to extend the frontier of the observable universe. Instruments with improved starlight filtering capabilities, higher resolution imaging, and more expansive spectral analysis tools will allow us to examine distant exoplanets with unprecedented depth. In addition to identifying biosignatures, they may one day detect technosignatures, signals, or structures indicative of advanced technology. With each successive mission and every quantum of data beamed across the void, we move ever closer to answering one of humanity's most profound questions. Are we truly alone in the universe?